title is a little bit presumptuous, apologize for that, but I honestly, probably like many of you that went into physics, I went into physics because for me, the chance to explain what is the universe was just fascinating. And so I remember many different instances throughout my career. There was this discussions about unifying the different theories of physics, trying to make compatible all the knowledge we have, and I used it to make predictions into the future of the universe. And so, will we ever have a theory of everything? I'll give you an answer in my last slide. But let me tell you what is the plan of the talk. The plan is, my plan is to talk a little bit about dark matter, to talk about general relativity and the Big Bang theory and its current status, to talk about dark energy and particularly look at the results from the Planck mission and the different observations from the Shu collaboration. I also want to touch upon the Higgs boson, the Large Hadron Collider, and the standard model of high energy physics, and then just one slide about quantum gravity, supersymmetry, superstrings, and all that. That's a lot of stuff. You're asking, do I know all that stuff? No, of course. I know a little bit. I have some information, I guess educated information, but it's hard to know all this. And then I'm going to concentrate on what's the current role of gravitational wave astronomy and what the future can bring from gravitational wave astronomy. And so, one of the things I remember reading about some time ago was about the end of physics. And I remember reading this. There was a statement by Lord Kelvin, a very famous physicist in the 19th century, and it was made around 1900. He said, there is nothing new to be discovered in physics now. All that remains is more and more precise measurement. Well, it turns out that it's not true. He never said that. Actually, what he said is in a lecture that was titled 19th Century Clouds over the Dynamical Theory of Heat on Light, was that there were clouds. And the first one was the difficulty in accounting for the results of the Michelson-Morley experiment within a description of light as a wave in the mechanical medium. At that time, physicists had this fixation with this concept that I just cannot get into my mind, this idea that it should be something totally different from all the chemical elements that we know in the universe, we call ether, which actually is a Greek word that means the breath of the gods. And but that was resolved. Do you know how was this resolved? Well, Einstein in 1805 said there's actually no ether. And he made a special theory of relativity, putting an equal footing with the laws of physics, at least on inertia frames of reference, the idea that the speed of light was the same regardless of the relative motion of the surface. When he did that, this first cloud was dissipated. And the second cloud was that there's, at least from what Lord Kelvin said, there seemed no way to date the equipartition theorem in the classical kinetic theory of gases and solids, no way to reconcile that theorem with the heat capacity to measure at low temperatures, which are well below the prediction of the equipartition theorem. And how was this other one solved? Please. Well, let me give you a hint. This is equivalent to saying that what it was known from the kinetic theory of gas, it couldn't explain black body spectrum. called the ultraviolet catastrophe of combining Boltzmann with the Wien's law. So how was this solved? Well, Planck came and said, well, maybe radiation is not continuing after all. It's emitted in quanta of light. And he postulated the existence of quantum theory of matter, and that's the way it was solved. So throughout history, there was a recurrent theme of trying to combine what we explain about the physical world in more comprehensive theories. The first one was Newton. If you think about what Newton did, he put together parabolas and ellipses. So he took Galileo's investigation that were independent from Kepler's about the inertia, the law of inertia, and kinematics in the 16th century, and put it together with Kepler's observations of the motion of planets. And when he did that, he developed Newton's laws of motion and the theory of gravitation. So that's probably the first successful unification in the theory on the history of physics. And the second attempt was Maxwell, combining Ampere and Faraday into electromagnetism. Just a few decades later, Einstein unified mechanics with electrodynamics in special relativity. And then again, just 10 years later, Newtonian gravitation with the special relativity and developed the general theory of relativity. All these are examples of unification. 1970, Salam, Glasgow, and Winder managed to put on equal footing and combine electromagnetism with the weak nuclear forces, incorporating the quantum, the electrodynamic of Richard Feynman developed 5 years earlier. And finally, by the 80s, it was accepted that you can put the strong nuclear force, the weak nuclear force, and electromagnetism in a combined theory that probably, it's easier to say non-unified theory than naming the symmetry groups. These are symmetry groups, but this is beyond the scope of what we're talking about. And all this was unified but of course, no GR. GR, general relativity, didn't get into the picture here. And I remember reading Richard Feynman's Lectures in Physics, which is a wonderful book. I strongly recommend you. You might think it's not very useful for your classes, but you can learn a lot of physics from reading Feynman's Lecture of Physics. And he mentions, there's a whole chapter dedicated to how would the theory of everything work. So he's trying to develop the theory of everything. He was interested. And that's one of the reasons that he went into gravity. And they're going to bring this in the slide later, what were the results of Feynman's interaction with the people working in general relativity, which is quite interesting. So let me start now, after this succinct summary of the different attempts to unify physics, with the dark matter mystery. Interesting enough, in 1884, Lord Kelvin, the same Lord Kelvin, estimated that the number of dark bodies in the Milky Way, many of our stars, perhaps a great majority of them, may be dark bodies. In 1906, Poincaré called this dark body for the first time dark matter. And the first to suggest the existence of dark matter using stellar velocity, calculated stellar velocities, was Jacobus Kapteyn, who made the first model of the universe, which you might see in some books. It looks like a flat disk with a globe in the middle. And actually that universe was our Milky Way, because that's what people thought was the entire universe 100 years ago. And then, of course, Oort, another famous astronomer, made similar calculations. They made many mistakes. The numbers, the estimates were probably too big. But this guy, Fritz Zwicky, a Swiss astronomer, working at Caltech pretty much all his career, he applied the virial theory to the coma cluster and the coma cluster of galaxies, and he made an estimation for dark matter, and he said it was 400 times more mass than was visually observable. So how do astronomers work? Well, before getting into that, Vera Rubin is probably the first one in making the most precise measurements of dark matter. And she published the results, well, first estimates in the 1970s and then 1980s, and then she found that most galaxies must contain about 6 times as much dark matter as visible mass. You're going to see that she was not too off with this estimate. We were pretty close. By around 1980, there existed some form of non-luminous matter was widely recognized as a major unsolved problem in astronomy. We're talking about barely 40 years ago. And this is the way it works. If all it was the matter that we see, the stars, then essentially the Newtonian potential, which gives the virial theorem, would be explained with curves like this. But what we get is this curve. These are from starlight, and these are from radio astronomy. And this is in particular M33 or NGC 598, a particular galaxy. But pretty much all galaxies exhibit the same behavior. And this is an interesting simulation. You need to observe it for a little while to see the difference between one and the other. They're hard to see when you first take a look. This one is a simulation, this is the real one, and this is without dark matter, this is the way it actually is. This spiral hypothetical galaxy will give this light curve, but the true one gives this light curve. One important aspect of dark matter, in any of the topics I'm going into in this talk could be a seminar by itself. And of course, we don't have time for that, but I want to point to just a few aspects of dark matter. One of the very important things is that dark matter does not interact with radiation. This is a very, very important point. For example, the bullet cluster consists of 2 colliding clusters of galaxies. And one thing that we can observe is that their center mass, we find actually 2 center of mass. One center of mass is the one related to visible and electromagnetically active matter, but the other one can see through gravitational lensing, and they don't coincide, they're separate. And so this is a good example that dark matter that does not interact with radiation. You may ask, well, what is it? Well, we don't know what it is, but we know it doesn't interact with photons. It doesn't emit light. And I mentioned the cosmic microwave background here because this is a very, very important aspect in terms of what dark matter is and how we can measure the content of dark matter in the universe. The cosmic microwave background is a result of the Big Bang in which our universe started. We're going to talk a little bit about general relativity and the theory of Big Bang, but one of the main results of the Big Bang is a result of this big explosion about 13 billion years ago. There's a remnant of when matter decoupled from radiation and photons could finally escape from matter that is called the cosmic microwave radiation. This is made in the microwave region of the electromagnetic spectrum because of the temperature. It pretty much has a black body radiation curve that is 2.7 Kelvin, which is very, very little departure from that. So this was predicted in 1948 by Alford and Herman, and it was found by accident by Penzias and Wilson. The guy who actually knew about the existence of the prediction of the existence of microwave background was Robert Dickey, who was a Princeton. And he built an antenna to detect it. At the same time, Penzias and Wilson in the Bell Lab, very, very close to where Robert Dickey was, built a similar antenna. They were trying to detect the cosmic microwave radiation. This was an antenna commissioned by NASA to follow satellites. And that's the reason why they use the ability to be sensitive in the microwave regime. Well, there's a book about just all the trial and errors, because one of the big problems that they had was a huge instrumental noise. They thought that it was because of the dust that were hanging around the antenna. And so they were even climbing up the antenna and cleaning, you know, all the crap from the dust. And then eventually they learned about this microwave radiation. They adjusted their instrument and they found the microwave radiation. By the way, something that you can detect, well, not nowadays with digital TVs, but if you remove your TV from your cable and from internet, and you happen to be in a place where there's no signal from a TV station, you're going to see a fuzzy thing moving around on your screen. A good fraction of what you see is the cosmic microwave background. And I don't remember who said, one of the people from the Dickey's group, but by the way, learned by phone that this happened and went to his lab and told all his team boys in school. And they said, you know, many people look for gold all their lives and they never find it. These people were just looking for shit and they found gold. They got the Nobel Prize for Physics in 1965. Well, what is interesting now about the cosmic microwave background and dark matter is that dark matter does not interact directly with radiation. It affects the cosmic microwave radiation, and maybe on large scales, and it has an effect on the density and velocity of ordinary matter, and actually creates something they call acoustic oscillations. You're going to see in the literature as BAO, baryonic, and baryonic because protons and neutrons and standard matter are called baryons. So it creates baryonic acoustic oscillations in matter that can be detected if you study the cosmic microwave radiation. And that means that ordinary and dark matter perturbations evolve in a different way, and they're going to leave different imprints in the cosmic microwave radiation. So let me go into general relativity now, which is the theory that first predicted the existence of the Big Bang. And it's a theory of gravitation, and I'm going to go into deep detail into describing the theory. Some of you here are taking my class in GR. But I like this statement by Carlo Rovelli, the guy working in quantum gravity. And I said, discoveries that space-time and the gravitational field are the same physical entity. So what we call gravitational field is nothing else than space-time. So space-time is the manifestation of the physical field. Another way of saying is that space-time is geometry, and geometry interacts with energy. It's an interaction. All this that is on the left-hand side of the equation represents geometry. This guy here is called a Ricci tensor. And the Ricci tensor is constructed with the quantity that is called the metric of space-time. The metric is what you use to measure distances. There's a lot. To measure distances, all you need is a ruler. Yeah, you need a ruler in flat space. If you want to measure the distance on a sphere, you can't use a ruler. You're going to use something that bends. How you bend it? Well, the metric tells you how you bend it. And adapted to the curvature of the space-time, you measure distances between 2 points. that metric, there's a particular way in which you take derivatives respect to all the other variables and respect to time. And you construct this guy here, which is called the Einstein tensor. This encodes all the information about the geometry of the space-time. See, this guy here on the left-hand side, the Einstein tensor, encodes all the information about the geometry of the space-time. And on the right-hand side, this other guy encodes all the information about the matter and energy content that there is in the space-time. So if you know this, then all you have to do is solve the equation for the metric and you find out the geometry. Sounds easier than to really do it. These are extremely complicated equations. There are 10 of them. There are actually 16, but due to symmetries, only 10 survive, the others are identical. The other 6 are identical. And they're highly nonlinear and coupled. So there is no systematic way to solve Einstein's equation. But something that you probably already learned by these stages in your studies, physicists love symmetries. Symmetries, we love it for a very good reason. They make our lives easier. So if we use symmetries, then, for example, a metric describing a space-time where the only physical parameter is what we call the radius of the universe. The universe itself is spherical. So notice there's only one function that is a function of time. I call it S. I didn't call it R because it's called sometimes the radius of the universe, so we didn't get confused with this other R. But this is essentially the size of the universe. And we assume that our universe is spherical. Notice that all I have here is these elements are the element of solid angle. This is the standard radial coordinate in the spherical coordinate. This, of course, the same. And k is a number that can only be 0, 1, or minus 1. Very simple. With these simple assumptions, and they're behind doing cosmology with Einstein's general relativity. By the way, it's the first time that we can systematically do cosmology. Since the time of the Greeks, and we assume that the Greeks were the first one in systematically start thinking about the universe, and that would be about what, 2,000, 3,000 years before our era, and we have about more than 2,000 now. So for 5,000 years, there was no systematic way of doing cosmology and trying to understand the universe. We have it for the first time. So one of the things that it was an immediate result of Einstein's equations when you use this metric, and that you have a universe that was expanding. In other words, you put this, which is only this term here on the left-hand side, not this term, and this term, the traditional Einstein equations, you put this type of metric, you solve the equations that are solvable. They're fairly simple with this symmetry considerations. And you find that at some point in the past, there was a singularity. So there was infinite density. The universe was a point. So there should have been a big explosion. And it started expanding ever. And Einstein didn't like that, and he added this extra term. This lambda is called the cosmological constant. He did this as a trick to prevent expansion because he thought that we live in a static world. In the 1930s, Hubble, using this telescope, found a very precise law describing the expansion of the universe. That the farther away the galaxies were, the faster they were moving away from us. The ratio of the velocity of the galaxies to the distance they have to us is a constant. It's called the Hubble constant. By the way, since 2 months ago, January this year, the International Astronomical Union decided that it has to be called the Hubble-Lemaitre law. It's because Lemaitre was a priest, but also cosmologist and astronomer that was the first one to systematically propose this model for our universe. So, if you put this in Einstein's equations, you get something rather simple. S dot means the derivative of the radius of the universe with respect to time by the radius of the universe. This is the radius of the universe again, cosmological constant. This is the density in the universe. And we can think of lambda as a sort of a fluid, and with an equation of state that would be that the pressure of the cosmological constant is like minus lambda. So we can move this to the other side where all the matter is. And then we get this equation. Notice all we have is a derivative of s with respect to time, s to the power 2, that's the radius of the universe. Everything else are parameters of the theory. And we can divide by this quantity, and essentially, because it would be s dot, which is a velocity, divided by s, which is a distance, that's a Hubble constant. That you could change with time, but we can look at a particular time, and it would be the Hubble constant. Let's say our time. And we get this equation. This is, again, Hubble constant. This is called the lambda cold dark matter model. And if we look at a particular value, which is the Hubble constant now, then the critical density would be the one that the factor rho is going to have now at our time. Using this value, we, in this equation, divide everything by this critical value. So here. By dividing this, we're going to get 1 at this time. And this is the equation that we get. This is the standard equation for the lambda cold dark matter model. It's a very simple equation. This is the quantity telling us if the universe is flat, or is hyperbolic, or is spherical. So spherical, it might get to a certain size and then start contracting and end up in a big crunch. If it's positive, the universe is going to expand forever, and if it's 0, that means the universe is totally flat. This other quantity is all the mass in the universe, the one that we can see, and the one that we're calling dark. And this is the energy content of the cosmological constant. So the data from supernovae and the cosmic microwave background suggests that we live in a flat universe. The matter content is about 0.3, and the other 70% is essentially dark energy. So, well, if we now write the energy density in terms of dark matter and the matter, the regular baryonic matter, that's the reason why we have a B sub-index here, then we get that B is about 0.04, and then the other one is about 0.26. So this is pretty much what also there Robin measured, 6 times more dark matter than observable matter. And so that would be 4%, 26%, and 70% lambda. These are rough estimates. And we're going to see that they're being measured more precisely. And this also is called the concordance cosmology, lambda cold dark matter. And so these curves are interesting because it represents the first confirmation, look, in 1998, that there was an acceleration and expansion of the universe. How we did that? Well, by being able to measure distance farther away than we never measured before, or measured with high precision at the distance that we measured previously. And so there were used 2 standard candles. One of them are what are called supernovae 1A. These have the peculiarity that when they explode, they have an intrinsic absolute magnitude that we know how much it is because it's the same in all cases actually is determined by the limit of the mass that the white dwarf companion of the binary system star can have. So because of that, we know exactly the absolute magnitude. Now, absolute magnitude is like having a bulb. You have a 100 watts bulb, you put it in front of your eyes, and it's going to blind you. But if you put it a kilometer away, you're barely going to see it. So the intrinsic luminosity of the bulb, the electric bulb, is going to be the same. But the apparent one is going to change depending on the distance. The same happens with the stars. We don't know how to measure distance to stars accurately beyond our local universe, let's say, beyond our neighborhood. When they're too far away, the phenomenon called parallax that lets us measure the distance to the star is too small because they're too far away. Essentially, what we take advantage, we know the distance between the sun and the earth. So we wait 6 months. That means from one side of the sun to the other side of the sun, we know the distance. We measure the angle that subtends to us, and that's going to tell us the distance to the star. But we can only do that when they're not too far away. When they're too far away, then it's a very precise method. So using standard counted supernovae 1A is a very effective method. There were 2 teams doing that, Rees and Perlmutter. They did it in 1998. They got the Nobel Prize in Physics because of that. Because they determined that not only our universe is expanding, but the expansion is accelerating. And they could only be explained by the existence of lambda, of the cosmological constant. And there were other measurements that contributed to these studies, and this is a recent paper by Rees, one of the guys that got the Nobel Prize, and Maki, who is one of our collaborators in TOROS, one of the PIs for the TOROS collaboration. And this shows very precise measurement on another type of standard candles that are Cepheids. Cepheids are stars where we can measure the period because they're variable stars. They vary a lot. Over a few days, they vary the intensity, the luminosity quite a lot. And so you can measure the period of the light that is changing, of the light curves. And they're related to the absolute magnitude of the star because they're intrinsic phenomena that happens in the star. So by measuring this and the apparent magnitude, then you infer the distance to those stars. And they can be used combined with the supernovae to make a very precise measurement of the Hubble constant and the expansion of our universe. And by the way, these guys, the guys that combine this work, like Rees and Markey and others, they estimated the Hubble constant around 72 in kilometers per second. And so all this is evidence of what is called dark energy. And what is interesting about dark energy is that it was in the 80s argued that the universe went through an inflationary phase. And I don't remember all the discussion that happened at that time, and they were quite interesting. And essentially they were saying the only reason why we look at the universe in any direction and we see, no matter how far away we see it to be looking the same, is because everything was connected. But right now, the universe is so big, and if we extrapolate to the past, it couldn't be connected. So they hypothesized a theory. The universe went through an exponential inflation too fast. In milliseconds, just expanded 100 times. And through inflation, they got to explain some feature. What is interesting is it seems that the inflation is corroborated by any observation that we have. But one of the interesting aspects of this is this. Up to 30 years ago, we thought that, the cosmological constant was very big here. But then essentially moved down to 0. And we started slowly expanding at a constant rate. Now, what was measured by Perlmutter, Rees, and all the different collaborations is that this is expanding. Again, notice here's the smooth. Here it wasn't, and here's not again. So this is what changed with cosmology over the last 30 years. Now, not only we have something that we don't know what it is, that is dark matter, but we also have something else in addition to that, but we know even less. We call it dark energy. Planck is a very recent mission that measured all this with exquisite detail. First was Covey. Covey in 1992 presented the results. This is Covey. WMAP was a different mission. So what it measured is the cosmic microwave radiation now, 30 years ago, with some precision, the one that they could afford at the time. Because of these contributions, they got the Nobel Prize. And WMAP is not 1992. This is 2001, 2002. Sorry about that. WMAP measured it again. You can compare. Higher precision. And then eventually in 2009, and with the last results released last year, 6 months ago, Planck measured with even more exquisite precision the anisotropies in the cosmic microwave factor. Why are these important? See, you can see them in comparison here. Well, they're important because essentially what we get is that we know now that we have a little bit more of regular baryonic mass than we thought, 4.9%. 26.8% is dark matter. And all this, 68.3% is dark energy. You know, a bit of a relief. It's not as big as it was thought, but it's equal. And these are other measurements in which incorporate the baryonic acoustic oscillations we mentioned before, the Rees measurements and the Planck measurements all come together to pretty much, these are the baryonic acoustic oscillations, the different peaks. Notice the dots are the observation. The blue line is the theory. It's beautiful. We can explain what we're seeing in the cosmic microwave background with exquisite detail. We don't know what it is, but we know a theory that can explain it. So the Planck's results are yes to inflation. We don't have gravitational waves, at least yet. And 3 very light, but with mass standard model neutrinos, and slightly slower expanding older universe. No evidence for spatial curvature. It's a little bit more dark matter and normal matter, but a little less dark energy. And as I said, this is a very precise result. Let me mention here about the gravitational waves. Could gravitational waves be produced during the Big Bang? Most likely, yes. Have they lasted up to the time of the coupling radiation, which is what Covey, WMAP, and Planck could measure? Maybe not. So maybe they don't see it, maybe we get to see that. And that's going to be quite an achievement. So let me jump into the standard model. The standard model of particles describe very well the atom, the nucleus, and the different particles. Essentially, what it does, it has all these elementary particles that make up neutrons and protons, and then we have these different types of neutrinos and electrons that are called leptons, all these. And the interaction between these guys are made by gluons, then all these other guys interact with photons, but there is another type of interaction that is dominated by this other type of bosons. They're not gluons or photons, they're bosons, Z and W bosons, and these are vector bosons, and the main problem with these guys, look at these, 0, 0, have no mass. These guys, they have mass. Because of that, it was postulated in the 50s there should be another particle that's going to explain why they have mass. And that was the case. And that is actually not a vector boson, but a scalar boson. Well, so far so good. But one of the problems that this standard model has is there is an imbalance between matter and antimatter. All the theories that we have in particle physics cannot explain that. It cannot be compatible with general relativity. It does not account for the accelerated expansion of the universe. No viable dark matter particles, at least compatible with observations. This is very important. And no account for neutrino oscillation. So we don't know, we measure, we observe neutrino oscillations, they can change from one into the other, but we don't know why that happens. And the standard model does not explain it. So, as you know, the Higgs was measured thanks to the Large Hadron Collider. More than 10,000 scientists work. See, this, we failed compared to this guy. We like we are up to 1,000, so 10 times smaller than this guy. Of course, we also spend much less money because the cost of Large Hadron Collider is $5 billion, and it's $1 billion in annual operation cost. Now, what happens is that the only thing that these guys did is confirm the Higgs boson. That was 2012. For 7 years after that, they tried to get new physics. Guess what? They didn't get it. Now that they commissioned the Large Hadron Collider, that was in December last year, and they're going to break it. So they're going to put more money, and is there a chance that they're going to see something? A lot of people are dubious. There was an opinion article in the New York Times by a person that they very much dislike now by the people working with the Large Hadron Collider. Is someone working in high energy physics. It's a woman, Sabine Honsenfelder. It's a German lady that writes beautiful, wonderful books, popularizing physics. I recommend The Problem with Math. It's a recent book that she published. And she argues that maybe they find something, but it's just way too expensive to keep pouring money into this guy that we don't know he had the chance of observing anything. What is they supposed to observe? Supersymmetry. What is supersymmetry? Well, we know that the standard model itself has limitations. So maybe another theory that uses symmetries, extrapolating from the gauge symmetries that we know that high energy physics obeys, could explain other features. And to do that, you need 25 more different elementary particles. All these particles have the same name as the one that I show you, and in 2 slides before this one, but they had the word S in front of them because they're supersymmetric partners. The interactions between them, maybe they could explain certain things. It's not very clear. They are having supersymmetry make very clear predictions as to what energy we could be seeing something. So far, no supersymmetric particles were found. By the way, a lot of people did their professional careers that were going to be found at LHC. That didn't happen. Let me talk a little bit about quantum gravity. And this guy, his name was Matvei Brownstein, very young guy, in the 30s. He's one of the first persons that started to look seriously into the quantification of gravity. And one of the first attempts he measured was a photon. It's quite interesting. Using Heisenberg principle that we know is at the core of quantum mechanics, you cannot measure with a precision the location of a particle, and with a precision the momentum such that the product of two positions are smaller than Planck's constant. Their products going to be higher. If you impose that principle to measure location and momentum in general relativity, and then it's a very simple calculation, you get that beyond certain length, you cannot do it because you will be creating black holes, tiny black holes. You cannot get information from there. And that's the size of 10 to minus 33 centimeters, which is the Planck length. So at the Planck length, you cannot say anything about the structure of the spacetime. And that's a big problem. We don't have a way to make quantum mechanics and general relativity compatible. Maybe because we have the wrong idea about quantum gravity, maybe because general relativity needs some changes of different formulas. And there are a couple of them. One is supersymmetry. The other one is what I call the quantum loop representation that essentially thinks that the intrinsic structure of space-time at the Planck scale is a form of loops, what's called spin form. I'm not going to get into discussing these theories. They have not made any observable prediction, not superstrings, not quantum gravity. And so, in the last 6-7 minutes of my talk, let me talk about gravitational waves. When I first came to the Valley, in 2 months it's going to be 23 years. When I came to the University of Texas, Brownsville. I made the Valley my home. When I came, there was only one other physicist, DJ Phillips, great guy, big, huge guy, who was teaching just at the community college. So I came to develop the physics program. And my specialty was general relativity, and particularly something very obscure, highly mathematical, called mathematical cosmology. And I had to develop a physics program. I said, I cannot develop a physics program with this or for this. I need to think about something else. And at that time, there was the LIGO detectors were being developed. It actually broke ground in 1992. So I thought, gravitational waves is the cool thing to do. Let's get into gravitational waves. And that's how I got my first grant while here. I got grants somewhere else, but my first grant I got here from NASA to do gravitational waves in 1998. With that money, we hired another guy, and we got more grants. And with that money, we hired more guys. With one of the largest group, the largest group actually, in Texas, in gravitational waves. So I saw that gravitational waves had future. I was pretty much alone. The only reason why UTV supported me because I was bringing money, but they thought I was crazy. Nobody could understand what we were trying to do here. They thought that they were just trying to count the number of angels in a pancake. And I remember people evaluating our firms saying they're trying to do something that we know is impossible, it's never going to happen. And, well, as you know, we had detected gravitational waves, 2 scientific campaigns got completed, but it was a long history of confusion and search. It took 100 years. It was very difficult. We didn't know, and let me show you in the next slide why. So, as I said, it was pretty much around when the LIGO labs were being built. Let me tell you, I was always interested in the history of gravitational wave detection, which started, more than 100 years ago. And when LIGO was about to be approved, at that time it was peanuts. It was $23 million. But still, it was a big fuss. Nobody wanted that money to be spent on something like this. Of course, the astronomers were the main enemies of doing this. And it was one astronomer, Anthony Tyson, that was a witness, presented testimony to the subcommittee of science from the Committee of Science, Space and Technology in the House of Representatives regarding the construction of LIGO, because it was a specialized NSF, the National Science Foundation couldn't fund it. They needed Congress to approve special assignment of funds to do this. This appeared in March 13, 1991 in the New York Times. And Anthony Tyson told all the representatives that were in this committee, they said this: imagine this distance. Around the world, 100,000 million times. The total is 3,840 billion of kilometers, or a million times the distance from Earth to Neptune. Take two small objects separated by that distance. Strong gravitational wave will modify less than the thickness of a human hair. It was an experiment. It's true. This is what we did. And he said there is less than a few tenths of a second to measure this. And we don't know if this event will happen next month, next year, or in 30 years. All this is true. And one interesting reflection about gravitational waves. Gravitational waves was a branch, if you want, of general relativity that was, a lot of people thought, well, okay, general relativity was great. We observed the precession of the perihelion of Mercury. Actually, it was observed long before it was explained. And GR can explain that. GR can explain a lot of things. But for a long time, people didn't see GR being useful for anything. Again, the first time it was truly useful is when the military realized that they had problems correcting GPS satellites because there were general relativistic effects, and they found out almost indirectly, and they had to contact the community, and they got to be using general relativity for precise timing with GPS satellites. But one thing that Einstein said, the problem when you are, and this is interesting, when we reflect about supersymmetry, supergravity, or superstrings, or even quantum gravity. He says, there exists, however, one serious difficulty is the lack of experiments. We're not going to get any experiments, so we have to take how to deal with problems where no experiments are available. And that's hard to do. And the attempt at mathematical rigorous solutions without guiding experiment is exactly the reason why the subject is difficult, but not the question. He said that after going to what's called nowadays GR1. It was the first conference in general relativity gravitation. They happen every 3 years. That was 1965, I think, in Chapel Hill, in North Carolina. And now, number 22 is going to take place in Spain this year. At that conference, there were just a handful of people coming. Feynman went to one of those, and he was very disappointed. And he wrote a letter to his wife, and he reminded me to not ever come again to this meeting for all your fine crazy people. And well, gravitational wave astronomy is a reality. It's only 3 years, 2.5 since the first detection, and we have now detected 10 binary black hole collisions and 1 binary neutron star collisions. So this is the first catalog. We have a catalog. And this representing all the different black holes, and here we have binary neutron star. What is interesting is posing several questions as to, these are the black holes that were found through X-ray astronomy because they're combining what I call X-ray binaries. They're, with masses that don't go beyond 10 solar masses. But look at all these. Most of the black holes that LIGO found, they're very far away. All the purple ones in our galaxy, all these were found very far away. And not alone, but colliding into other black holes and forming heavier black holes. They have larger masses. So there's a lot to be explained in terms of the stellar population, why this is happening. Also, having found the first neutron star is also quite interesting. So there was August 17, 2017. That marks now not only gravitational wave astronomy, but the beginning of multi-messenger astronomy. And by the way, one of the things I'm very proud that we managed to be part of that. And see, the one here is UTRGV people. So we have several of you guys here, our students, Moises, Richard, when we're here, that were here, and in a paper that was published in a combination of about 20 papers in dedicated volume of the Astrophysical Journal Letters that was published. Just look at the date. It's only 2 months after the detection. And actually, we submitted our paper 2 weeks before the publishing date. Never in the history of my career I got a paper accepted so quickly. It was really, truly historic. As I said, it's a very important volume, and piece of history, a new field of astronomy has started with this. See, this was our particular observation of the event. Here is binary neutron star measured, which we call the kilonova in the optical regime. This is the galaxy here. You can barely see here, but the galaxy is attracted to be able to do the analysis. And so it evolved very fast. You can see here, you look at the dates, and you can see how it's very bright the first day. In just a matter of 5 days, it's gone. No other phenomenon that we know of in nature has this behavior in terms of the electromagnetic emission. And this is an interesting cartoon that shows, first, well, this is the line of sight. So this is the way we're drawing and thinking that the observer is in this direction. So first, we get the gravitational waves that are coming, slightly before the collision. And the collision happens just minutes after this, and then the collision, we call it the time t0, and just a couple seconds after t0, we get gamma jet, what's called a short gamma ray burst, and then we get an emission in the optical, ultraviolet, infrared. This is just in a matter of days, and the same picture now, and we can see it in X-ray radius up to months. And all this has been detected. This is one of the most interesting phenomena predicted over the last 50 years that has been observed with exquisite detail. Now, one of the interesting things about this is it can explain the abundance of the very heavy elements. We cannot be explained by supernova explosion alone, and it cannot be explained by the production from regular stars like our sun. But one interesting thing, the gravitational wave does, and we're coming full cycle from where I started now, is the measuring of the Hubble constant. As I mentioned before, this green, light green, is a Planck measurement. And this, which is 60-something, 67, then this is the measurement of the supernovae 1A and the Cepheus, and has larger uncertainty, but their number, most probable value, 73, 74, falls here. We have a lot of dispersion in our measurement. It's only one measurement. When you get an optical counterpart to gravitational wave, you measure redshift from there, but also the one thing that is extremely important, when we detect the gravitational wave, there is something called the chirp mass that it goes frequency and distance to the source. So we have the distance to the source, and it's an independent way of adjusting it, and which means we can measure Hubble constant. Of course, we have 1 point, so we can barely, get true valid statistics, but it falls in the middle of the two values. We're going to need several more years of observing these events, but that can improve dramatically our estimates of the Hubble constant, and maybe help elucidate the difference between the two measurements. So there are several remaining riddles. Why this GRB associated with binary neutron star merger lasted less than 2 seconds, and it's not too much energy. What did we get? Well, for one thing, we're both neutron stars. We believe they were, but we're not sure what got is a black hole. There's a good chance that what we got is a very massive neutron star at the end. And then what is the event rate of this kind? How often it's going to keep happening? You only got once. Well, notice that right now, this past Monday, it started the engineering run that are going to go through the entire month on March for the live on video detectors, and on April 1st, we're going to start the third observational campaign. Notice the ranges, let me just focus here on binary neutron star range. During 01, it was up to 60 megaparsecs. During O2, it was at 80 megaparsecs, and we got the first binary neutron star detection. Now we're going to be 50% farther away at 220 megaparsec range. From this other big dome, and this is in Colomacon, in Salta, in Atacama, at 4,650 meters high. Construction is ongoing right now, and at the little village that is at the foothills of this mountain, 1,000 meters below, 3,000 feet below, we have. This is going to be our control room. This is an old photograph. It was finished now. This is going to be the control room. So we're going to be ready to observe when all three launches with the telescope that I showed you. You know, we bought all this here in the US and we shipped it. So the previous slide was showing how they assembled and they were testing the dome. And so I promised you that I was going to tell you if we ever going to have 50-year recovery. Well, I think there are hopes that we might. It won't happen soon. It won't happen in my lifetime. There's a good chance it won't happen in your lifetime. It's going to take a while. And the important thing is we're getting to learn more and more and more. And particularly with this area, gravitational waves, there's a lot of work for a lot of physicists like you. I just Googled primordial black holes and gravitational waves. Actually I didn't Google, it was only in the archive, which has some selection mechanism. Not every crazy guy can send papers there. They have a sort of a preliminary refereeing system. 202 papers in the last year. Because people think that primordial black holes could be what dark matter is all about. We don't know if that's true. Could be. And there's another paper that appeared in Nature, I think this week, and it claims that proving the existence of ultralight bosons with a single gravitational wave measure. Of course, the frequencies are too low. It's going to have to be done by Lisa. But it's just the beginning. So I think there is hope for a theory of everything. And this is the future. Lisa. It's a mission from NASA and the European Space Agency. NASA quit about 10 years ago and now decided it's cool and they need to go back into this, put a gravitational wave antenna in space. This is going to measure very low frequencies. Einstein telescope. This is a project of the European Union. It's going to be 10 kilometers long, so about 2.5 times larger than LIGO on Virgo. And it's going to be underground. It's going to be cryogenic. It's going to be a new generation of detectors. It might take another 20 years until it's built. But we're going to see, by the middle of this century, new instruments that are going to be probing the gravitational wave nature of our universe. This is observation, this is experiment, and this is the reason why I think there is hope.